Okay, let's unpack one of the truly mind-bending questions in modern biology. How does an animal that has to fly nonstop for weeks, sometimes even months, over the open ocean handle the fundamental biological need to sleep? I mean, we're talking about creatures that literally cannot afford a single minute of vulnerability.
It really does sound like a contradiction, doesn't it? Sleep
Mhm.
deprivation causes these severe cognitive deficits in pretty much every animal we study.
Mm-hmm.
You get impaired navigation, reduced vigilance, even hallucination. And yet,
Mm-hmm.
we know swifts, sandpipers, and some of these iconic seabirds they defy this logic. They engage in these prolonged, nonstop aerial journeys.
And that's exactly the mission of this deep dive. You, the listener, are getting the shortcut straight to the definitive answer. We're drawing from a groundbreaking scientific article that used neurophysiological recordings, so actual brain activity data, to settle these long-standing assumptions about how, or even if, these flying giants managed to get some shut-eye in the air.
And our star subject for this is a truly magnificent bird, the great frigatebird, Frigata minor.
What a creep.
Absolutely. They are these incredible flyers, but they're also ecologically locked into continuous flight. They have extremely long wings, but their feet are poorly webbed, which means that once they land on the water, they really struggle to take off again.
So they're basically forced to stay airborne for weeks or months at a time, just soaring over the Pacific.
That's right.
The logistics of that alone are incredible, but the real feat here is the methodology, right? It's one thing to guess they're sleeping up there, but how did the research team actually capture hard data, an EEG, from a bird flying thousands of kilometers over the ocean?
It was a monumental achievement in animal tracking. I mean, really. The researchers deployed these specialized data loggers. They're called the Neurologger 2A.
Yeah.
And they integrated them with GPS tracking and the 3D accelerometer. The entire package weighed, get this, only 55 grams.
Only 55 grams. That's lighter than a golf ball. That minimal weight is so critical, obviously, but it's amazing that a device that tiny could capture this kind of data. And what exactly were those loggers focused on recording in the bird's brain?
They were recording the EEG directly from a region called the hyperpallium.
Hyperpallium.
Okay, so for anyone who's not a biologist, the hyperpallium is essentially the primary visual processing hub in the bird's brain. And this is a really critical detail because staying airborne, avoiding obstacles, navigating it all relies so heavily on vision. So monitoring activity there tells us immediately about the bird's level of conscious awareness.
They attached these tiny data centers to breeding female frigatebirds, flying for up to 10 days straight, covering distances up to 3,000 kilometers from Genovesa Island in the Galapagos. That setup let them compare brain activity in the air versus, when the birds were safely nested.
Okay, so before we get to the findings, what was the established theory? What did everyone think was happening?
The common, almost universally accepted assumption was something called unihemispheric slow-wave sleep, or USWS.
The one-sided brain sleep. Exactly. It's this fascinating evolutionary strategy where an animal sleeps with only one hemisphere of the brain at a time, and the corresponding eye, the one connected to the awake hemisphere, is kept open and directed toward the environment to maintain vigilance.
Ducks do this, right? And dolphins.
Ducks do it, dolphins do it. And the hypothesis was that flying birds must rely on USWS to maintain aerodynamic control and, avoid a fatal crash.
So with the EEG data in hand, what was the central finding? Did they confirm it?
The central finding was definitive and very exciting. Great frigatebirds do sleep in flight. The neurophysiological recordings show these clear EEG patterns of slow-wave sleep SWS, and these patterns were fundamentally similar to those recorded when the birds were resting safely on land. It just settled the debate right there.
But it wasn't just the single hemisphere sleep everyone was expecting. This is where it gets a little more complex, isn't it?
Exactly. They observed two distinct types of SWS happening in the air. First, the expected unihemispheric SWS, where one hemisphere was clearly sleeping. But, and maybe more surprisingly, they also detected bihemispheric SWS, or BSWS. Meaning both hemispheres were sleeping simultaneously.
Wait, they were fully asleep with both sides of the brain at once, while actively gliding thousands of meters over the ocean. That seems terrifying.
It is, but they were doing it. And there's one more layer here that's just astonishing. The researchers also detected these fleeting episodes of apparent rapid eye movement sleep.
REM sleep.
REM sleep. That's our deepest phase of sleep, where we dream. In humans and most animals, it's characterized by total muscle atonia. You're paralyzed. If a frigatebird went into full REM, it would just plummet into the sea.
That's right. The total atonia was suppressed. So here, the REM sleep manifested as just a momentary dropping of the head and a brief twitch, and the mean duration of these episodes was incredibly short, averaging only 4.92 seconds. It's not a restful dream state, it's more like a lightning-fast biological reset. Wow. So we have these brief flickers of a REM, and we have both uni and bihemispheric SWS. When did all this rest actually happen? Was it just continuous, day and night?
No, the sources are really clear on this. Sleep occurred almost exclusively at night, which makes sense, right?
Yeah.
The demands for active foraging are slightly reduced in the darkness. And crucially, sleep did not happen when they were engaged in active, energy-intensive flapping flight.
Okay, so they don't fall asleep while they're putting in the physical effort.
No. Sleep occurred mainly when the birds were soaring or circling in rising air currents, thermals, and then followed by these long, straight glides. They're using the physics of the atmosphere to facilitate rest. They find the most stable, energy-efficient moments to doze off. And we also saw that the sleep occurred at slightly higher altitudes, on average about 159 meters compared to their awake altitude of 135 meters.
Buying themselves a little margin of safety.
A little buffer, exactly.
Okay, now let's pivot to what I think is the really crucial finding here. If they can manage to sleep with both hemispheres, BSWS, while gliding, why bother with the unihemispheric SWS at all? Let's connect that vigilance function to the actual flight path.
This is where the asymmetry data provides a huge insight. When they're safely on land, their SWS is, relatively symmetric. Only about 48% of their land sleep was asymmetric. But in the air, that number just skyrockets. SWS was significantly more asymmetric, totaling over 71% of their in-flight SWS.
So they're actively choosing or biologically prioritizing half-awake sleep most of the time they rest in the air. It's a trade-off. They give up deep, symmetrical sleep for heightened vigilance.
Precisely. And the genius of the study was linking the brain activity to that 3D accelerometer data, which tracks the bird's exact movement. They found this very distinct pattern. When the birds were in USWS, they were more likely to circle or turn towards the side that exhibited the greatest slow wave activity.
Meaning toward the side that was sleeping more deeply.
That's it.
Wait, that sounds backward. If you're turning left, you'd expect the left side of the brain to be awake and steering. Why would they turn into the sleeping side?
This is the aha moment, and it requires knowing a little bit about bird neuroanatomy. In birds, visual input almost completely crosses over in the brain. The right eye primarily feeds the left hemisphere, and the left eye primarily feeds the right.
Okay, so let me get this straight. The sleeping hemisphere is connected to the eye on the opposite side.
Right. So if the left hemisphere is sleeping deeply, the right eye, which feeds into that sleeping hemisphere, is likely resting. But the awake right hemisphere is getting all its input from the left eye. So by turning toward the deeply sleeping hemisphere, the bird ensures that the eye connected to the awake hemisphere is facing outward, away from the body of the tern, actively scanning the horizon.
That is incredible. They are essentially using the one-sided sleep as an autopilot mechanism. The sleeping side is steering the turn while the awake eye stays pointed outward, scanning for threats, maintaining their soaring pattern. They are watching where they are going while they sleep.
That's the perfect summary. It confirms the primary function of USWS in flight is attention and environmental awareness, not just, basic aerodynamic stability. We know this because they can glide successfully while in BSWS fully asleep. If attention wasn't the driver, they would just sleep with both hemispheres and get deeper rest. The fact that USWS dominates proves that the ecological pressure for vigilance is just paramount.
That sets up our major paradox beautifully. We've established they can sleep while flying, and they have this sophisticated half-awake system to manage it. But now we have the quantitative results, which are, frankly, paradigm-shifting. We need to talk about how much rest they actually get.
The numbers are stark, and they really do challenge decades of biological assumptions about how much sleep you need. The total time frigatebirds spent sleeping during their massive aerial journey was minuscule, only 2.89% of the total time recorded.
Okay, let's put that into a 24-hour cycle so we can really grasp the scale of that restriction.
It averages out to 0.69 hours per day.
So about 41 minutes.
Roughly 41 minutes of total sleep in a 24-hour period.
41 minutes a day. For up to 10 days straight. To put that in context, the average human needs 7 to 9 hours. Even African elephants, which are considered extreme, sleep for maybe 4 hours. 41 minutes it's nearly nothing.
It's jaw-dropping. They were existing on this unbelievably limited budget of rest. And it wasn't just the amount that was low, the quality was also reduced.
Okay, give us the breakdown on quality. What did the EEG data show about the depth of their sleep?
The SWS bouts, so the individual segments of sleep, were much shorter in flight. They averaged only about 11 seconds. Compare that to nearly 30 seconds when they were on land. And on top of that, the intensity of SWS, which we measure by slow wave activity power in the EEG, was lower across the board.
So if we use an analogy, on land, they're plugging into a high-speed charger for 8 hours of deep restorative rest. In
Yeah.
the air, they're getting just a shallow, like 3-second trickle charge every hour or so.
That is a perfect way to visualize it. They're getting minimal, extremely brief, and shallow power naps. And yet they are maintaining these complex tasks, foraging, following ocean currents, navigating thousands of kilometers without the catastrophic cognitive breakdown we'd see in any other sleep-deprived animal.
This really does challenge the core tenet of sleep research, which argues that large daily doses of intense sleep are required for performance. These frigate birds have found a biological hack.
They absolutely have. And it forces us to ask, how are they not accumulating a crippling sleep debt? In humans and most mammals, that homeostatic process, the sleep pressure, it just builds up relentlessly. You get tired, your cognition decays.
So what does the study tell us about that pressure? Did the debt just disappear?
No, and that's the key. The debt was clearly still present. When the frigate birds finally returned to the safety of the nest, their sleep intensity immediately spiked and then declined over time. That is the undeniable physiological signature of releasing built-up sleep pressure. They were catching up.
So the body knows it needs to recover, but something is overriding that urgent need while they're airborne. They're somehow able to forestall this crushing homeostatic demand until they're safely back on solid ground. It's like they hit a biological snooze button on the debt.
That's it. And that ability to resist the effects of sleep loss is driven by these extreme ecological demands. We see similar, though less dramatic, resistance in other animals, like male pectoral sandpipers, who virtually eliminate sleep during the hyper-competitive mating season. But the frigate bird takes this resistance to a completely unprecedented level for sustained periods.
This has been a fascinating journey into the neurobiology of endurance. We've confirmed that birds, like the great frigate bird, can sleep in the air, using both USWS for vigilance and BSWS for deeper rest, cleverly tying their half-awake sleep to their navigational soaring.
But the truly revolutionary finding is the massive sleep restriction they endure. Less than an hour a day for sustained periods. These birds show us that complex cognitive performance can be sustained on minimal, brief, shallow power naps over many days. That's something once thought impossible for a high-functioning animal.
So what does this all mean for you, the learner, the person trying to manage performance in a demanding world?
I think these findings provide critical information on animals that have evolved these specialized neurochemical mechanisms to maintain performance on minimal sleep. If these birds can successfully delay the overwhelming homeostatic need for recovery, we have to ask, what specific adaptations allow them to resist the effects of sleeplessness? And, what could studying their ability to forestall sleep debt tell us about improving human cognitive resilience, or even developing new treatments for sleep disorders? That ability to hit the biological snooze button, that is certainly something worth mulling over.